Hey everyone, kestava back. Sorry for the delay. It's been a couple weeks. I was away on holiday, but we are back with a new problem. This time it's going to be steel design. So let's get out our AISC steel manual. Mine is the 14th edition. You know, the 15th edition for you new students is out now. So I'm guessing anyone in college is going to have that teal colored manual, but I will be using the 14th edition, the maroon manual, in today's example. Not too many differences though, so should be able to follow along pretty easily. All right, so today we have a propped cantilever shown here, 12-foot span, and then the cantilever is 5 feet with a point load at the end of it, P. That point load is distinguished between 1,000 pounds of dead load and 1,000 pounds of live load. And we are asked what's the minimum W section required to adequately support that load. So first we want to start. So for steel, you want to choose what type of loading criteria you're going to be using, how you're going to be designing. So is that going to be ASD design or LRFD design? So for steel, we know that we can choose either, and both are adequately fine and just as easy to use. In this example, I'm going to be using LRFD. So I like to use LRFD when I can, except for wood. We always know wood, you want ASD. But anyway, side note, sorry. So our load combination that governs is 1.2 dead load plus 1.6 live load. Again, you can find this in your local codes or the AISCE 716 manual. That's where you can find all your load combinations for your LRFD. But again, this load combo governs. We plug that in. We have a P of a factored P now of 2.8 kips at the end of our cantilever. All right, moving on. Now, you could do method of sections and stuff like that and cut this beam in multiple spots to get your moments and your shear diagrams, and then use that to then solve for your required W section. But something that's handy to have that a lot of engineers use is actually our steel manual. And we want to pop open to table 3-23. These are our common shear, moment, and deflection equations for standard or common patterns of loads. And if we flip through here, believe it or not, you have cantilevered sections, you have simply supported sections, you have fixed conditions, you have different loading patterns. But if you look here on page 3-222, you have a beam overhang, overhanging one support, aka this is also called in the field a propped cantilever. So you have your prop, then you have your cantilevered edge, and then you have a point load at the end of it. So that's perfect. That's the exact loading situation that we have here. And then you have broken down very simple equations that have been proven mathematically to solve for various conditions. So we want to know our M max and we want to know our V max. Well, there's two different shears. So V2 is the largest shear, so that's what we want to solve for. So V2 equals P. So we know P equals 2.8 kips after it's gone through the LRFD load combinations. So that's our max shear is 2.8 kips. And then we have an M max at R2. So you can see down here, our moment diagram. M2 is at R, or M max is at R2, which is at the propping point of the cantilever. So at the end of the cantilever, we have our maximum moment, which equals P times A. A is just the length of the cantilever. So if we swing back over to our example, get my book out of the way. Our A distance is the 5 feet. So that's our propped cantilever. That's our cantilever length. So P times A equals MU, where A equals 5 feet. Boom, 14 kip feet. So that's our MU, and VU just equals P, which is 2.8 kips. Done, done. All right, moving on. Let's choose a W section to test out. I think it's just easier to explain to you guys when you grab a section that you think might work out. You get better at guessing when you do more problems and have been exposed to more situations over time. So I'm deciding to try a W10 by 15, and you can run through quickly, check the yield strength of the section. So ZX, which we can find, again, in our steel manual, you can flip on over to table 3-2, and this is your, basically, I have it tabbed as my Z table, because this is categorized, how it's set up is actually from smallest to largest Z sections. So if we pop here, W10 by 15, your ZX is 16 inches cubed. So your yielding, after we focus, your yield strength is 16 inches cubed times your Fy. So ZX times Fy. That's your so your ZX is your plastic section. Fy is 50 KSI. And that gets you 800 kip inch times phi of 0.9, divide by 12 to get it into kip feet, gets you 60 kip feet. So so phi mn for yielding is greater than mu. So we're okay there. So that sounds great. So we have a section that we know might work out, at least for the first check. That's the quick one. So the second check is lateral torsional buckling, which we have a pretty lengthy span of 12 feet where it's unbraced along that entire span. So for lateral torsional buckling, that's going to reduce the capacity of our section quite a bit. So that's the next thing we need to check. And in order to do that, first we need to check if our member is compact or not. So the reasoning behind that, again, if we flip back over to our AISC manual, we want to go back, solve for flexure. So if you go to chapter F, design of members for flexure, it's pretty straightforward. That's what we want. And you go to table F1.1, which is just the next page. You want to go, this gives you all your criteria for each type of steel member that you might be designing for. And we have a W section, which is like this I shape. So we have we have a bunch here. So we have F5, we have F4, we have F3, and we have F2 sections. And it all depends on flange slenderness and web slenderness, which is it compact, is it not compact, is it slender? So we need to check our compactness of the flange and the web, and then that will determine which one of these sections we get to use in order to design our member. Sound clear enough? Okay, good. So we actually need to go back to table B4.1B, which is in section B4. There we go. And there's two tables here. So there's members subject to axial compression, and there's members subject to flexure. We want flexure. And we need to do two things. We need to check compactness of the flanges. So we have our example. So here's our W section. Sounds good. And if you look down here, it might say, oh, well, what about this one? That also looks like it too. If you look closely enough, I don't know if you'll be able to see it in the video. Let's see if I can zoom in for you without freaking out. Come on. Nope, not going to get it. Okay. But these are actually built up sections. So there's no radii where they would roll the steel together and combine it. This is just built up sections of steel. Whereas this one has a rolled section here. So that knows you have a true W section, so that's what we want. So this is for our flanges. We need to make sure, check our B over T. Our B over T comes from your properties at the beginning of the book for your W10 by 15, and that's 7.41. Now you need to check your lambda P. I don't know if I said that Greek symbol correctly. It might not even be lambda, but stick with me here. We're going to call it lambda. So lambda P, you need to check that, and lambda R. Start with lambda P. Just use this equation here. E is 29 times 10 raised to the 6th psi for steel, and Fy of 50,000 psi. That comes out to 9.15. And now, if we go back, I'm going to step through everything with you. So go back one page. For flexure, so this is member properties. Compression elements shall not exceed the limiting width to thickness ratio, lambda P from table B41. If the width to thickness ratio of one or more compression elements exceeds lambda P, but does not exceed lambda R from table 1B, this section is non-compact. But if we go, back a little bit. Let's see. Its flanges must continuously be connected to the web or webs, and the width to thickness ratios of its compression elements shall not exceed the limiting width to thicknesses ratio, lambda P. That means it would be compact. So lambda P is greater than B over T. So we know our flanges are compact. Now, if we go back one more page, or forward a page, excuse me, we also need to check to make sure if our web is compact. So we want to go here. Webs of doubly symmetric eye shapes, that's us. You need your H over TW, and you need to solve again for lambda P, which is now this equation. H over TW you can find from your properties at the beginning of all your W sections. 38.5, lambda P equals 90.5. Lambda P is greater than H over TW, so it means your web is compact as well. Both are compact. So our W10 by 15 is a compact section. All right, cool. So moving on. That means if we go back to flexure in chapter F, compact, compact. Flange is slender? Nope, it's compact. Web slenderness? It's compact. That means we get to design with section F2. And we know that it's actually kind of nice. Tells you what the limiting states are, which limiting states is just what is the mode of failure that will cause, what will be the mode of failure. So what will give you, I guess to make it really dumbed down, is just you have an MU, an ultimate moment that's being experienced in the beam. What is the smallest phi MN? And that will be produced by either yielding or lateral torsional buckling. So section F-2, yielding is just Mn equals MP, or plastic moment, which equals FYZX, because that's the plastic section. Well, we've already solved for that previously, and we know that that equals 60 kip feet, which is greater than MU of 14 kip feet. So we know we're good there. That checks out. So next we need to check lateral torsional buckling. I wish this was simple. It takes a little bit of time, but we're going to keep going here. I'm just going to get us caught up. Here's yielding again, just so everyone remembers. Lateral torsional buckling, you have a couple things you need to check. You need to grab LP, LR, and LB. Oops, and I have a quick mistake here. LB is your unbraced length, is your largest unbraced length. So if we go back, our largest on brace length, LB, is 12 feet. So that's easy. So that's 12 feet. And then LP and LR, if you actually flip to the next page, it gives you these really, really complex, well, first one's not so complex, but LR is super complex equation. And actually these are given to you in your Z tables. So if we flip all the way back to our Z tables, thank goodness, you can see we go to our W10 by 15, and you have LP and you have LR. So we have both of those, so that's nice. And we know that LB is greater than LR, which means that phi MN equals FCR SX, which is our elastic section. So if we go back to our, there's a lot of page flipping. So if we go back, so LB is greater than LR. So there you go, what I just said. And FCR now equals this beefy equation, but we're almost to the end here, I promise. So this beefy equation here, and what's nice is that if you keep reading on to the next page, you want to look for some hints. So right here, if you see user note, the square root term in equation F2-4 may be conservatively taken equal to 1.0. All right, cool. So that's what we've done here. Instead of solving for all that garbage, we're just going to say that's roughly 1.0. What does that leave us with? Well, CB, we also know is 1.0. If you would go back, again, this is section F2. And it talks about, in section F1, general provisions, talks about your CB and all your cases on what that might be. And if you read through this, you'll find, oh, actually it says right here, for cantilevers or overhangs where the free end is unbraced, which we have, CB equals 1.0. So that's why CB is 1.0. Still read that whole section to know when different things apply. Your E is the same. Your LB is still 12 feet. Break that down into inches. Keep everything the same unit-wise, so 144 inches. And what that gets us is all the items we are going to be needing in order to solve for RTS. I'm going a little fast here, so let me just bring it back over to you. We have our big equation for FCR here. Phi MN for lateral torsional buckling equals FCR times SX. SX, you can just pull from the from your properties table for your W sections. So that's that. FCR was this big long equation. We know the square root, all that can be just summed to equal 1.0. We know everything else besides RTS. So we just said all of these. That's every other part of the equation, or variable in the equation. RTS squared equals IYHO over 2SX. That is given. Starts off here, but if you come all the way down and keep reading, it breaks down all the way to this equation here. HO is just D of the section minus thickness of the flange. IY, you can find that in the properties section. So RTS equals 1.01. That means everything plugged in here. FCR equals 14 KSI. Phi MN equals FCR times SX times phi of 0.9 divided by 12 to get you 14.6 kip feet. The 12 just gets you from kip inch to kip feet. We know that that is greater than MU of 14 kip feet. So we're good. See how much it reduced from your yielding scenario? Yielding scenario of 60 kip feet to your lateral torsional buckling scenario of 14.6 kip feet. So there's your big difference there. And lastly, we need to solve for shear. Shear is pretty straightforward. We need to go to AISC chapter G. That's 16.1-67. And we go G2. That's your shear equation. If you flip to the next page, you know all your variables besides CV. For webs of rolled I shapes members, which is what we have, where H over TW is less than that, you know that CV equals 1.0. So we check H over TW, which again is in our properties section. That comes out to 53.9. H over TW is 38.5, which is less than this, which comes out to 53.9. So we know that CV equals 1.0. And actually, we know that phi equals 1.0. So instead of 0.9. So this is actually a mistake. Don't mind me there. Area of web is just thickness of web times your D. So that's all that takes. Plug all those in to your top equation here. Phi Vn equals 112.5 kips, which is much, much larger than Vu of 2.8 kips. So we're good. So we know that the W10 by 15 is adequate. And just by analysis, you might say, oh, well, what if, or observation, you might say, well, what if there's a smaller W section that we could use? Well, if we, for the shear, yeah, that definitely would make sense to check another one. But for our moment capacity and lateral torsional buckling, they were very, very close. So we're gonna say that that's the smallest W section that we can use for this case. So that's it. Thanks everyone. No, it's a longer video, but please like and subscribe if you liked what you saw here today. As always, I've partnered with Brave ad blocking. So if you would like to see more ad-free videos, which I'm going to highly keep to myself to keep pushing for that, please sign up with Brave and feel free to tip if you'd like what you saw here today. That way I can keep on moving here, give you more and better content. But until next time, thanks everyone. Bye.